All right, everybody, we're going to go ahead and get started here. Welcome to our Cassini Grand Finale webinar. We are so excited that you are here joining us. We're joined by a few other members of the StarNet team, Ann Holland, James Harold, and we're joined with our friend here, Colin Mitchell. He is a research associate on the Cassini mission. So before we get into some of the meat and potatoes of the webinar and start talking about different ways that you can integrate this event into your programming, I did want to mention we have our poll up there. It looks like 22 folks have responded so far. So if you have not yet responded in the poll, go ahead and do that. Also, go ahead and introduce yourself in the chat box so everybody can say hello and know where you're from and what your role is. So maybe say your name, where you're from, like your location, and what your role is at your library. And once those results start pouring in, we'll go ahead and get started. All right, so we're going to go ahead and broadcast those results. I was just asking, if you're already planning any programming related to the Cassini mission, and it looks like a few folks are, and then a few of you guys are waiting to see what this webinar is like, to see if maybe it's something that you can do with your library. We do have a lot of great resources, a lot of hands-on activities, and I'll show you where to find those here in just a moment. So let's go ahead and view these votes. All right. I know some of you guys probably had so much Eclipse programming, so much Eclipse mania, you're still a little exhausted from that. We certainly understand. All right. So we might reopen that poll kind of at the end of the webinar and see if your results have changed. All right, so everybody, my name is Brooks Mitchell. I'm the education coordinator here at Space Science Institute, or National Center for Interactive Learning. And again, I'm joined by a few different team members. And we just wanted to kind of give you a brief introduction to what we do at StarNet. And I did want to start out by, of course, offering our condolences to some of our friends and colleagues in South Texas and Louisiana that have been affected by Hurricane Harvey. We know some folks at the Johnson Space Center down there and the Lunar and Planetary Institute. And you guys as librarians, of course, I'm sure a lot of libraries were affected down that way too. So, just keep it on your radar that those libraries down there may need our help in the future. So with that, of course, we do want to thank our sponsors for our different programs that we can do here at Space Science Institute, the National Science Foundation, and NASA. Of course, we appreciate their support so we can do these programs. And we want to point you in the direction of StarNet. StarNet is kind of our online community for different librarian professionals and to kind of get STEM programming and STEM resources to you guys. We just are trying to kind of bridge that gap between STEM resources, NASA resources, different tech and engineering resources, and bringing that to librarians, and also providing a community for you guys to have dialogue with each other about what's working, maybe what's not working, what activities you're having a lot of success with. Oh, guys, and I do want to note this webinar is being recorded. We're going to upload the version onto YouTube, hopefully within a day or two. So just a heads up that this is being recorded. So here I have a list of all of our professional development resources that have, or some of them actually I should say, that have come up recently or are coming up in the future. We do have a lot of webinars coming up. On September 13th, we'll be joined by some friends at the Lunar and Planetary Institute to do a webinar all about hands-on activities. On September 9th, we'll be partnering up with the After School Alliance to talk about one of their successful programs, Lights On After School. And on October 4th, we'll be joined by Brian Day, who is a member of the NASA team. He is the lead on citizen science there, and he's going to be joining us for International Observe the Moon Night. And you can actually click on these links within Adobe Connect, and it'll take you to the registration page for those webinars. I'll be sending out links after the webinar to all of you guys on the registration list. So yeah, I'll be sending out a list of all these links as well. So we just completed our first how-to video, or one of our first how-to videos. We're very excited about that. Check that out. It's on YouTube. It's for a very fun activity, the scale model of Sun and Earth. StarNet will be at conferences coming up soon. Arcel, Aztec, let's see, the Mountain Plains Library Association. There's a lot of them coming up, so make sure to check our list on StarNet. And if you're run out of time and you can't watch this whole webinar, or you want to go see some of the webinars we've done in the past, follow that YouTube link, that links to our StarNet website, and we'll show you some of those webinar resources. Okay, just wanted to point you guys in the direction of the STEM Activity Clearinghouse. This is where we have kind of, I want to say, curated some specific STEM activities that are perfect for a library setting. So these are designed specifically for libraries, and within our STEM Activity Clearinghouse, we have different collections for different events. Of course, we have a lot of activities for the Eclipse, and now we have some activities specifically for the Cassini mission. So if you're looking for programming ideas, head over to our STEM Activity Clearinghouse and check out our Cassini collection. Okay, and just a few last reminders. Make sure to follow us on social media. We have a really, really good Facebook page. Our web content manager does a great job. Follow us on Twitter, too. And sign up for our newsletter. It goes out about once a month, and it provides a lot of really great updates for a lot of our resources. After this webinar is over, you'll be directed to a SurveyMonkey link. Please fill that out. We love getting feedback on what we can do better with our webinars, what's working, what's not working. So you guys kind of help us, figure out how to craft our webinars. So fill out that SurveyMonkey link, and at the end of it, you'll get a certificate of attendance if you need that for professional development for attending today's webinar. Okay, so with that, I'm going to quickly turn it over to Ann Holland. She's going to talk a little bit about Cassini and why we are here today talking about it. Thanks, Ann.
Hello, musical chairs. Thank you, Brooks. All right, first off, thanks everybody for coming. We're really excited to have this kind of different webinar than we normally provide, where you're going to get a chance to interact with one of our scientists here at the Institute, Colin. We'll get to him later, though. So really quickly, before we dive into the webinar content, I did want to give you a quick overview of the Cassini mission to Saturn. I'm not sure how many of you even had heard of this mission before we sent out this webinar announcement, so we're really glad that you're here. So let me quickly give you an introduction to the mission, and then Brooks will share with us again some of those hands-on activities, and then we'll head over to Colin, who will let you know what I might have got wrong in my description of the mission. So the Cassini-Huygens spacecraft began development in the 80s with the goal of studying Saturn, its moons, such as Titan, the planetary ring system, and Saturn's very mysterious atmosphere. The mission was launched in 1997 and achieved orbit in July of 2004. Shortly thereafter, the Huygens probe detached from the spacecraft and plunged towards the surface of Titan, completing the first ever landing in the outer solar system and providing us with unprecedented views of the surface of a moon other than our own, and I would like to say probably a much more interesting moon than our own. 20 years after its initial launch, the mission is finally coming to an end, with the spacecraft scheduled to crash through the Saturnian atmosphere on September 15th, taking measurements and making new discoveries until either it's destroyed or it can no longer transmit, or both at the same time. Today's webinar is going to provide you with some hands-on activities to help your patrons celebrate this momentous event in NASA history. And we'll also be hearing about current science mission content from Dr. Colin Mitchell, who is Research Associate at the Space Science Institute and a Cassini Mission Associate here at our location. So now I'm going to go ahead and pass you off to Brooks Mitchell. He's going to walk you through some of the activities. Please keep the questions coming down there in the comments. And do remember, if you see anything cool in the slides as we move forward, you can actually progress backwards through them to go catch those links, or Greg will also be posting some of them down there in the chat. Brooks?
All right. Let me just get our Elmo cam set up right here. Excellent. So guys, the first speaker over here. I want to show you just kind of a fun little craft activity that you can do to kind of help build some excitement for the Cassini Grand Finale and for the planet that it has been observing and researching for these past few years. So this is Make a CD Saturn. Let's see, let's go to the next slide. And Greg's going to provide the link for you right down there, and that'll link you to our clearinghouse. So it's a pretty simple craft, and all you really need is an unused CD, okay, a small, about 2-inch in diameter styrofoam ball. You'll need some glue. I just have a glue stick here. I might recommend maybe something a little bit sturdier, maybe some Elmer's or some super glue. You'll need a toothpick, a paper clip or some type of hanging device, and some needle nose pliers. Help, not 100% necessary, but they really help. So if you have these around your library, this will be good for this craft. So the first step is have your students decorate this styrofoam ball. I might suggest a really soft paintbrush. And of course, you don't want to really provide too many limitations. You guys are at libraries, so there's a lot of open-ended learning. So however your students want to decorate it, they can. Of course, it would be nice if they could get some of those features of Saturn on there too. So after they've decorated their styrofoam ball, take an adult, have one of your library staff or another adult volunteer separate it into two. So you have two halves. Okay, so you have a fully decorated Saturn with two halves. Next thing you'll do, find a unused CD. It's 2017, so I bet that's pretty easy to find. And have your participants decorate this if they'd like. One suggestion I saw on the craft activity sheet was to put a little strip of glue, like a little line of glue, and then decorate it with black glitter, so it'll kind of show those gaps in the rings. I have one right here that I've done that I've kind of been showing everybody in the office, and it is not decorated, but I still think it looks pretty cool. So for the rings, if you have the glitter, if you have the materials, it would be nice to decorate it, but you don't necessarily need to make a cool Saturn. Okay, so after you have your two halves right here, and you have your CD, go ahead and put some glue on it. And you really only need to put the glue kind of in this middle area. And that's not really what's going to hold. It's going to help hold the styrofoam balls together, or the styrofoam halves. So you just want to get it kind of right there. Place one styrofoam half on one side, place another on another half. And go ahead and take a toothpick just to really make sure that it's staying in there. Place it between that little gap in the CD. So from here, you can use your pliers, or you can use some scissors. Again, I would have an adult do this, or volunteer, and just kind of cut off the end of the toothpick. That went better than expected. All right, so we have our CD Saturn now. You'll have one styrofoam ball on this side, or half on this side, the one half on this side. You have your rings right here, but we're not quite done because we want to create a mechanism so that this can kind of be displayed, right? So it can be hung up, maybe even like made as a Christmas tree ornament or something like that. So you might think, just put this paper clip, right? So this is kind of just like a little hook. Just put it right to the top, but you're actually going to want to put it at an angle. Saturn is tilted at, what is it called, 27 degrees?
27 degrees.
27 degrees. So you don't want it to hang up like this. You want it to hang up kind of like this. I don't know if you guys can see that on the Elmo cam. I'll show you over here. You want it to kind of hang up at this angle. Might be a little small. So maybe half an inch to an inch from the very top, from the North Pole, if you will. Place this paper clip. Try to get it through that middle hole of the CD. And then from here, you can use your pliers to kind of bend the end a little bit, just so it really sticks in there. You don't have to do it too much, just so it sticks in there really good. It will create a little bit of a mess just with this styrofoam, but besides that, it's a pretty easy craft, and it can get your participants excited about Saturn. So now I have two of these guys to hang in my office. I'm excited. All right, so I'm going to turn it over to Jamie Harold, and he's going to show you an opportunity for 3D printing that kind of relates to the Cassini mission. Jamie?
Do we have those links?
Yeah, Greg's going to post those in the chat box.
So we spent a little time looking around at 3D models of Cassini that you might be able to print for those of you with 3D printers. So there's three I found. So this is the guy who made it. He called it Teeny Cassini. And it's not fully accurate, so he didn't start with a CAD model of a spacecraft. But one of the things you'll notice about a spacecraft is that They're not necessarily great for 3D printing. They have a lot of fiddly bits that makes it really tough. So even this guy, what he did is he cut the spacecraft in half so that you could do it in 2 halves on your printer and then assemble it like that. Now, depending on what you're printing with, what kind of plastic you use, I actually find that doing something in half like this and assembling it and making it look good, it's actually pretty tough. But an alternative, if you don't want to do that, is just to print the halves. And I bet if you put a little magnet on the back there, you'd have a lovely little Cassini refrigerator magnet that you could distribute to people. This also comes with a conveniently removable Huygens probe, which just tried to deploy to the table.
We dropped Huygens again.
Yeah. There goes Huygens. So this is the first. This is probably the easiest of the ones I found to print, probably because it was designed to be printable, not to be accurate. The second is from NASA, and so if you've got an enthusiast, or if you just want to make one to show around, but if you've got a really enthusiastic 3D printer person, this one has, I think, over a dozen parts to it, plus a lot of pegs for assembly. And I didn't try to make that one, but it's probably the best mix of sort of accuracy and printability you're going to get, but it's going to take you time. So that's your sort of weekend modeling activity if you want to get into that. And the final link, and it's only up here as a cautionary tale because it was the first one I found on NASA. I don't recommend trying to print this. It's simply a dump from a full CAD model of the spacecraft into a 3D printer format, including the ultra fine antennas. And there's no remote way you're going to manage to print that. And I don't care how much scaffolding you try to use for it. So again, in order of those links, that Thingiverse one is probably the easiest, and I would probably recommend the refrigerator magnet strategy. You can have people argue about which half they get. And then the second one would be good if you want to do a really serious model and put a little time into it. There you go.
All right, thanks, Jamie. All right. Now, and while I'm closing up, did you want to make mention about the Museum Alliance opportunity?
Yeah, thank you. So Greg is going to post in the chat box there a blog post link back to our website that has another opportunity that the Universe of Learning out of NASA is going to provide for you guys to learn a little bit more about some sort of different Saturn science and what Colin is about to talk to us in a few minutes here about. So Greg just posted that there. I did just want to warn you, which is why I got back on to talk about this, that if you are not already a member of the Museum Alliance, you will need to register for that site before you are allowed to join the webinar. So you might want to do that sometime this week because it sometimes does take a few days for that registration to go through. But regardless of if you want to go watch that Cassini webinar or not, I would definitely recommend you go check out the Museum Alliance and register for that site. They do provide a bunch of professional development opportunities. They are not meant specifically for librarians, but we do have a pretty large library contingent on there now, and I'd love to make it a little bit bigger. So thank you, Brooks.
Great, thanks, man. All right. So again, we are joined here by Dr. Colin Mitchell. I insisted that we call him Doctor. He's very humble.
Yeah.
And as we are going through, or as he's going through his presentation, please enter any questions in the chat box. I'm going to be sitting here. I'm just going to be recording your questions, and after we get done, we'll have a little Q&A at the end. So, Colin, do you think those 3D printing Cassini models, would that be like a good Christmas present maybe for some of your colleagues?
That's for sure. Why not?
Yeah, we're gonna get some printed and you can take it to the grand finale. So I'll just give you a little bit of a background on Dr. Mitchell here. No relation. He is a research associate here at the Space Science Institute, and he works on the Cassini Imaging Central Laboratory for Operations. We just call it Cyclops. And there he works on analyzing some of Cassini's Saturn ring images. He helped plan the Cassini mission, and he works on calibrating the Imaging Science Subsystem, the ISS instrument. And he's going to talk a little bit about some of his research, some of the great things, really interesting things that they found and discovered. So I'm going to turn it over to him. And again, please, if you have any questions, just go ahead and enter them in the chat box. I'll record them, and then we'll ask him at the end of his presentation. Bear with us just
Technical
one
difficulties.
second. We pulled the webcam out, so we're going to get that put back on. Let's see. All right. And guys, maybe just put a yes in the chat box if you can see us right now. Okay, great. Sorry. So yeah,
It took me
Go
literally
for it.
half a second to break it. That is awesome.
We appreciate it.
Okay, I'm good to go. All right, so thank you, Brooke. Thank everybody.
yeah.
I'm Colin Mitchell. I work here at the Space Science Institute. I work for the Cassini imaging team. And yeah, I plan the observations. I study some of the aspects of Saturn's rings. And I study the plume of Enceladus, which we'll be talking about in a little bit. So, first let you see what Cassini looks like. So this is a little diagram of the Cassini spacecraft. Where is the... There we go. All right. So as you can see, fairly complicated thing. Most spacecrafts are. They got lots of things attached to them. What we're going to be talking about is, the science involved, right? So I've got all of the instruments listed on the right. There's a lot of detail in here you really don't need to know, but you've basically got three different types of instruments on this spacecraft. You've got the stuff at top, which are the telescope-like instruments. ISS is the Imaging Science Subsystem. It's highlighted in yellow because it's the one that I work on. But all of these are basically telescopes of one form or another. And then you've got the radio instruments. We've got a little radar, and we've also got an enormous dish here on top, which we can fire radio waves at things. And so we use that in order to study things like Saturn's atmosphere and the rings and whatnot. And then finally, we've got a whole bunch of instruments which are the in situ instrument set. Basically, these are the instruments which study Cassini's space environment. They study the plasma surrounding the spacecraft, they study the magnetic field, and we even have a little dust analyzer down here, so we can collect particles that are orbiting Saturn and we can analyze them. So here's an image just basically for scale. It's a really big spacecraft. These little things down here are of humans. And so it's roughly the size of a small bus, give or take. What I normally tell people when I don't have an image is that this dish up here is 10 feet across. This is the high gain antenna. And this thing on the side here, that is the Huygens probe, which we dropped onto Titan, which I'll be telling you more about in the future. Okay, so we launched the spacecraft in 1997, like Ann was saying. This is a picture of the launch here. This is a Titan 4B, which was basically the biggest rocket we could find. But it's a large spacecraft, and we have a long way to go. And so it took us 7 years to get there, and we had to do 4 flybys in order to do it. We did 2 flybys of Venus, 1 flyby of Jupiter, and 1 of Earth, too. And we arrived in 2004, and the main mission, the prime mission, was designed to last for 4 years. Okay, but yeah, this is NASA. We usually design things to last longer than their prime mission, right? We like to keep going. And so we finished the prime mission in July of 2008. The spacecraft was healthy. It had plenty of fuel. So we said, okay, let's just keep going. And so we did another 2 years mission, which we called the Equinox mission because it was equinox at Saturn during this mission. We finished that up. We were very happy, and the spacecraft was still healthy, and we still had fuel, so we kept on going. And we started what we're calling the solstice mission, because what we're doing is we're trying to get to the next solstice on Saturn. I'll show you a diagram about what Saturn seasons are like in just a second. And that mission is currently ongoing, but of course, like they said, it's going to end in September 15th when we crash the spacecraft into the planet. And I'll be answering why we're doing that in a little bit, too. No, just cliffhanger. All right, so here's another image of the launch. It was a night launch. I'm told it was very spectacular, but it's a pretty picture. And on the right here, this is basically the path that we took in order to get to Saturn. So we launched from Earth here. We did a little flyby of Venus, right? So first thing we did was we fell into Venus, did a flyby. That put us on this little red trajectory here. So we did a loop around the sun, did another flyby of Venus, then we did a flyby of Earth, and then we did a flyby of Jupiter, and then we finally landed at Saturn 7 years later. So it took us a while to get there. The outer solar system's hard to get to. They talk about Mars. You can launch a spacecraft to Mars every 18 months or something like that. Yeah, Saturn's a lot harder to do. All right, so this is the diagram showing you what the seasons were like at Saturn. So it turns out Saturn has a very long year. It's about 30 years. I like to tell people I'm like 1 1/3 Saturn years old, something like that. So whenever we arrived in 2004, it looked like this. And basically, the Saturn has a tilt just like Earth's, well, very close to Earth's. And the seasons at Saturn were, it was winter in the northern hemisphere whenever we arrived, and it was summer in the southern hemisphere. Okay? So we orbited around for a while, and then we did the Equinox mission. During the Equinox time, of course, it went from summer and winter to fall and spring, respectively. And this is a very neat time because at this point, the sunlight, if you can imagine the rings are like a plane, the sunlight is going along the plane, so there's no real direct illumination of the rings, and that has interesting effects, which I'll tell you about later. And then now we're basically over here where it's reversed seasons. It's summer in the northern hemisphere and winter in the southern hemisphere. And actually, the solstice was just a few weeks ago. And so we timed it so that the crash happened just a few weeks after the solstice, which is nice. All right, clicking through. All right. And so this image, this pair of images, these were 2 images with basically the same viewing geometry, but they were taken about 10 years apart. And what's happening here is the spacecraft is in is in Saturn's shadow. Okay? And so if you were to look in the sky for the sun is actually behind Saturn somewhere over here in these images, or down here in these images. And what's fun about this is, first, you can tell which season it is, because if you look at this one, the rings are down covering the southern hemisphere of Saturn from Cassini's perspective, right? So that means that this is at the start of the mission. And in this one, the rings are covering the northern hemisphere of Saturn. So this means it's very late in the mission. And one thing I'd like to draw your attention to in these images is this big, fuzzy torus-looking thing like this here. There we go. That is the E-ring, and I'll be talking more about that later. It's one of the ethereal rings of Saturn, which you can't see it from Earth, actually. And so this is one of the reasons why we like this viewing geometry. At this part where the sun is backlighting everything, you can see things that you just can't see from Earth. All right. So here's a diagram of the Saturn system. Saturn has got a lot of stuff orbiting. It's basically a little mini solar system. Instead of the sun, you've got, a planet and some rings, and then you've got a whole bunch of moons orbiting it. The number of moons, I'd actually have to check again because it keeps increasing. But the last one I remember, they named number 60. That was a few years ago, and I know they found 1 or 2 after that. So we've got 60 some odd moons. They're basically large balls of ice and a little bit of rock or something like that. Most of them are fairly small, but some of them are large enough to become spheres due to their own gravity. And that would be these guys up here, like Tethys and Enceladus. These medium-sized moons, I guess, because Titan's huge, but these are medium-sized moons. We call these the icy satellites because they're mainly made out of ice. And then we got a whole bunch of little ones. And then, of course, we've got Titan. Everybody loves Titan. It's a giant moon. It's bigger than our moon. And, of course, it's got a nitrogen atmosphere. So there's that. That's very exciting. And in this talk, I'll basically, I've got to cover 13 years worth of stuff in like 20 minutes. It's hard. So I'm going to have to cut things and narrow it down a little bit. But yeah, I'm going to be talking about mainly Enceladus. We're going to talk a little bit of the rings, then talk about Titan too. All right, so here's Enceladus. And there's 2 very interesting things about Enceladus. The first thing is that it is an extremely bright moon. Okay, so we measure how much light gets reflected off of something, and we call that the albedo of the moon. And Enceladus has got an albedo of about 80%. That means that if you shine a bright light on Enceladus, 80% of that light comes back at you. Okay, and that is roughly equivalent to fresh snow. So it is extremely bright. We normally think about asteroids and things of these dull, dirty things out in space. No, Enceladus is nothing like that. Enceladus is basically a snowball. Okay, for comparison, Earth's albedo is typically around 30% because we've got a lot of cloud cover and clouds are very bright. Something dark like the moon might be 10% or something like that. So it's very bright. Why is it bright? Well, the reason it's bright is because it's geologically active. It actually has a region at the South Pole. Let me just point that out right here. This is the South Pole. And these features, these linear features that you can see, here's one right here. There's 4 of these. And we call them tiger stripes because they kind of look like tiger stripes. But what they actually are cracks in Enceladus' surface. There are these many-mile-long cracks, and what's great about them is that there is material erupting out of them. And so basically, Enceladus has a bunch of geysers at its south pole. All right, and you can't see it in this image, but if you carefully maneuver the spacecraft so that you get the right viewing geometry, remember how the rings were only showing up because of the right viewing geometry. If you do that to Enceladus, you get images like this. Now, this is one of the first images of Enceladus' plumes. And what we've got here, this image requires a little bit of an explanation because it's a little strange. Because, what's up with this bright background sky, right? I mean, space is supposed to be black, right? What's going on there is Enceladus is inside the E-ring. So that big fuzzy torus that was made up of little ice particles that I told you about at the beginning, Enceladus is in the middle of that. And so what we're seeing is a bright background E-ring, and we've got a nice dark moon embedded in that. So basically the viewing geometry of this is the sun is kind of, you can tell by the crescent, the sun is off to the bottom left. It's just outside the field of view, basically, like 20 degrees outside the field of view. And so this is Enceladus' crescent, and all of this stuff is the plume, which is composed of lots of small ice particles being emitted from the tiger stripes.
And just to clarify, this is H2O, right?
H2O. This is water ice.
Okay.
Now, you can't tell that from these images, but Cassini has also got those instruments that allow us to detect the space environment. And one of those is a dust detector, so we can collect dust particles and analyze them. And yes, these are absolutely water ice particles.
Wow.
Yeah. Very cool. Yeah. And you can tell both from the direct measurements of the dust detector and by the properties of the light scattering that they do, these particles are really tiny. They're about a micron across. And a micron is 1,000th of a millimeter. So they're really, really tiny things. Like it takes like 100 of these to go across a human hair. They're really, really small. All right, now, like I said, this is an early image of Enceladus. This was taken during the Prime mission when we really, we had suspicions that Enceladus was weird, but we didn't really know all that much about it, right? And so during the extended Equinox mission and the Solstice mission, we've been able to, rearrange the orbits and whatnot in order to get much better viewing geometries of Enceladus, and that's what the next image is. So this is Enceladus' south pole, and again, it's a crescent shape because you need the right viewing geometry to see the particles, and you can see all of the tiger stripes and the stuff erupting out of them. And so this is basically a row of geysers here. There's one here, there's one over here, there's one over here, and there's one just kind of off the field of view over here. And so the idea here is, we've tracked, this down to about 100 individual sources along these tiger stripes. And so the idea is that there's some reserve of water underneath them that is boiling off like a geyser. And so we kind of jokingly, we call this, cold faithful. All right. So this next image here, this is just here because it's pretty, quite frankly. So this is an image taken at nearly the same time as the last one I just showed you, except it has Saturn's limb in the background. That's what this is. Yeah, we do occasionally take pictures that are pretty. We are allowed to do that on occasion, which is good because it'd drive us crazy if we couldn't do that.
Right.
All right. So this is the closest view of Enceladus' surface that we ever took. This is an image which is about a little over a kilometer on a side. So it's 13 meters per pixel, and it's a 1,000 by 1,000 camera. And this is the region around one of these tiger stripes. So the tiger stripe, it's hard to see, but it's this feature right here that's running across from left to right. And as you can see, there's lots of stuff going on down here. It's very geologically active. There's a whole bunch of ripples and folds and whatnot. And there's even boulders, all these little bright spots that you can see around here. These are basically individual boulders on the surface of the moon. So, and this is the best view we've ever gotten. And right now, actually, the South Pole is in shadow because of the seasons, and so we're never actually going to get any better than this, I'm afraid.
Colin, how far away was this picture taken from? Do you know?
Oh, I could work it backwards from there. it's a ways.
Okay.
We did a thing where we sped past the moon, and the problem was that we had to leave the shutter open for so long that it would blur the images, right? So you have issues with that. And so what we actually did was, during the pass, we rolled the spacecraft to counteract the blur.
Okay.
And
Okay, nice.
Yeah, so it's very hard. Yeah, the people at Cornell worked all that out. It was very impressive.
You scientists. So clever.
Yeah, they do all sorts of crazy things. Yeah. All right, let me go to the next slide, please. There we go. Okay, so, if these are geysers, geysers are hot, right? You imagine there's probably, some heat source underneath. So we should be able to check that, right? So we have got various other instruments on Cassini that can map things in the infrared. And so what I've got here is we've got a map of the polar terrain. This is made from ISS images. And we've overlaid a heat map of the terrain on top of that from the Sears instrument. Excuse me. And as you can see, again, red and yellow are hot, blue is cold, and so you see lots and lots of heat, and it falls right along the tiger stripes, which is very nice. And if you zoom in, later images, it does a very good job of landing just right on top of the tiger stripes. And so we think this is a nice indication that we've probably got liquid water underneath there. All right. And another thing about these plumes is, like I said, we've got instruments that can sense the space environment and analyze stuff. And whenever you analyze the plume, whenever you fly through it, you can analyze it. You get this. So we find a fair amount of water vapor, methane, things like that. We also find simple organic molecules. We've got carbon monoxide. And we've got larger stuff, so we've got things that have more than one carbon in them, and of course we got carbon dioxide too. And so this is fairly exciting. You've got water, you've got heat, you've got organic molecules. If you're interested in looking for life off of Earth, this is a prime candidate here. And so this is probably the biggest discovery of the mission, as far as I'm concerned. Other people could disagree or not, but I think this is the biggest deal of this mission. And so we've got a model of Enceladus here. This is what we think it looks like. We've got basically you've got a shell of ice, it's about 50 kilometers thick, and then underneath that you've got a global ocean underneath that that might be 10 kilometers thick, and all that surrounds a rocky core down here. All right, shifting gears a little bit. That was Enceladus, but we're talking a little bit about rings now. The way to bridge the gap is to talk about the E-ring. So it turns out if you're launching stuff out into space from a moon, it ends up somewhere, right? So it doesn't just disappear. And it turns out that what's happening is Enceladus is creating that E-ring that I was talking about. This is an image from one of those mosaics that I showed you earlier. And this is like the edge of the E-ring is what you're seeing there. And this black dot right about there, that's Enceladus. And this really, really bright thing underneath it, that's the plume. And all of these interesting features, these, we jokingly call one of these the curly Q, and then we got this one here. These features are formed by the ice particles as they're being launched out away from Enceladus. And what's really neat is, we can take this and, we can apply our knowledge of celestial mechanics to it, and we can actually reproduce these features. This slide on the right here, this is a simulation that I did with Carolyn and some other co-authors, where we can basically launch particles off of Enceladus, figure out what their orbits are, and we can reproduce all the features of this image. That's the one slide in this that I directly.
Hey, Colin,
It's the best slide.
It's an awesome slide.
My favorite.
Yeah. Could you speak for a minute about creating that mosaic? And so when we see this image, this isn't a single snapshot.
That particular image is.
That is, okay.
Yes, and so the mosaic, I forget the exact numbers, but I believe it was 24 footprints.
Okay.
And so we have a field of view on the wide-angle camera of 3.5 degrees.
It's not very much, right?
It's about, it's not huge. It's about 7 full moons across, something like that. It's a few fingers at arm's length, so it's not very big. And so in order to make a image like that, what you have to do is you have to take lots of images next to each other, and each time you take one of these images, if you want it to be color, you also have to take it in different filters.
Okay.
And so typically we'll take, a red filter, a green filter, a blue filter, and a clear filter in order to make those images out of it.
Okay. Very cool.
Yeah. There's actually quite a bit of art to that. It's not just science.
Right.
All right. Okay, so going down to the main rings, we have found things in the rings which we're calling propellers. Now, these are objects which were predicted in the past, but they'd never been seen before Cassini, and so it is pretty exciting. What these objects are, if you can see one, it's moving from the bottom to the top of the field of view. It starts about here. There it is, and then it moves on up. And what this is a ring particle that is unusually large. Now, most of the particles in the rings are about human size. Think volleyball, beach ball, something like that. Something about yay big. But there are some larger ones, and if they get up to a certain size, they start affecting the particles around them. And so what this is a particle where it has basically cleared out a little bit of region around it, so that there's a big bright thing in the center, which is the actual particle and probably some other stuff that's glommed onto it. And then you get basically a void on either side of it. And that's what these dark patches are on the rings. Okay. There are literally thousands of these. If you check out this image, if you look at this tiny little patch of the ring here, you get this image. And then if you look at these tiny little patches of the tiny little patch, you can see all these propellers in them. And so there's literally thousands of these things. We've been tracking them now for years, and basically, if you study the rates at which they orbit Saturn, it tells you how these particles are interacting with the ring environments. They're very cool because of that.
Can we take a question real quick? Christina was asking, how much bigger are those propellers compared to some of the other particles?
Okay, so you can get a propeller from something hundreds of meters across, something like that. Yeah, the average particle is maybe about a meter, and then the things that we're seeing here, a huge one might be a kilometer. Okay. What happens, turns out, is that as you make the main particle that creates the propeller larger, the propeller gets bigger and bigger. And what happens is, if you make the particle big enough, the propeller starts extending all the way around the rings, and it meets up with itself. And so if your particle gets large enough, you end up with a gap instead of a propeller. And so we actually have 2 moons that do that in the rings. So here they are. This little moon right here is Pan. It forms this thing called the Inky Gap. It's 28 kilometers. Pan is 28 kilometers across. The Inky Gap is a few hundred kilometers across. And then there's another one. This one is actually discovered by Cassini. This is, my arrow went away. There we go. This one is called Daphnis. And what's interesting about Daphnis is the gap is narrow enough that as the ring particles move past Daphnis, because everything's moving in the rings, right? The further away from Saturn you are, the slower it moves, and so there's this differential motion of everything in the rings. As the particles move past Daphnis, they interact with it gravitationally, and it forms these little wakes down here. So this is little waves in the rings created by Daphnis. Okay, and then there's the equinox, of course. In this image, the sun is basically in the ring plane, and so the sun is doing very little to illuminate the rings. And all this stuff over here that you can see, that is Saturn's shot. What's happening there is that the sun is shining on Saturn, so Saturn's bright, and then Saturn shines on the rings, and then we see the light from the rings based from that. If you look over here, there's no Saturn shine over there, right? And so it's extremely dark. This is because there's no sunshine again. Except for in a few little places, you can see there's stuff here, there's little stuff here. And what's happening is you can imagine that the rings are more or less flat, but in a few places there are these waves in the rings. So there's a little portion of the rings that's going up and down. And these are basically caused by moons gravitationally perturbing the rings. And so in these images, we were able to see these features caused by the moons tweaking the rings just a little bit. All right. And if you look inwards at the C and the D rings, these are, let me back up and show you where these are. This is this portion right about here. Okay, so the stuffing very close. No, they're actually not. They're not perfectly circular. They've got lots of waves on them, actually. It's very neat. So the rings interact with the moons of Saturn, and so this tends to create little radial variations in the rings as you go around them. Turns out that this one, I'll be talking about this in a second, this one has got a little tweak to it. It's elliptical, so it's got an n=2 pattern on it, if you know what that means. Oh, this one is. So the B ring here, that one is an ellipse. This one out here is basically a smoothed out pentagon.
What?
Yeah, it's because it's got a it's a little more complicated than that, but it's got a resonance with another moon and it's causing these radial perturbations. Wow. Yeah, it's really hard to see, but you have to get your spacecraft. You have to carefully measure everything in order to see it. But yeah, it does have this wave feature at the edge of the rings.
Very cool.
All right, so we're talking about this part of the rings right in here. And come on. There we go. All right, and so you can see it's got this regular pattern of stuff on it. Basically, this portion of the rings looks like a vinyl record. You've got grooves in it. And what we think is going on is at some point in the past, roughly around the time Voyager was observing Saturn, we think what happened was that a comet struck Saturn at that time. And with the comet came a bunch of dust and gas and things like that. And so we think that what happened was this gas and dust hit the rings and just barely perturbed the rings. And then after that, it started winding up and you end up with this vinyl record pattern. You can actually measure how fast this thing is winding up. So the D ring here you can see at all times. The C ring you can only see at equinox, but the D ring you can see and measure, and we've seen that it started winding up sometime in around 1980. Come on. There we go. You were saying? Oh yeah, and okay, so this is the edge of that ring that I was saying was an ellipse. And what's really interesting about this is you can imagine that, you've got this material at the edge of the rings, it moves in and it moves out. And whenever it moves out, it's not a problem, right? It just kind of spreads out and does its thing. But whenever it moves in, there's already material there, right? And you get a traffic jam, right? Things kind of pile up. And the effect is that you get these basically mountains at the edge of the B ring. These are composed of the little ring particles, and they're we saw these during equinox first, and there you can see the shadows that they cast here. These are about 2 miles high, give or take. Right. Although, yeah, I don't think you could actually hike them because they're made out of little things and they're constantly changing.
You would need some crampons to get into that.
Yeah.
Rebecca, I see your question. I'll upload, as long as it's okay with Colin, I'll upload some of these to SlideShare, and I can share that link with you after the webinar.
Oh yeah, that's perfectly fine.
Just shoot me an email.
Yeah. Okay. And so finally, we've got Titan. Titan's, this large moon. It's roughly the same size as Mercury, and it's got a nitrogen atmosphere around it. And the sad thing was that whenever Voyager flew by Titan, we weren't really expecting this, and so we looked at Titan, we saw a giant fuzzball. Not very exciting. But the good news is that because Voyager was able to analyze Titan's atmosphere, we know what it's made of, and now we can take Cassini's instruments, and whenever they designed the instruments, they were able to choose filters for the imaging instruments that are able to see through this haze. And so Voyager, Titan was a fuzzball. For us, we can see down to the surface, which is this. And so you got all sorts of different color variations and whatnot. There's light areas, there's dark areas. It's hard to say exactly what causes the light and dark areas, but it's not that interesting. The cool thing is that well, it's just terrain. Sorry, I'm not a Titan guy. And so you've got all these features. What's really exciting is that there are lakes on Titan. So these are not water lakes. Titan's temperature is about 90 Kelvin, so water is about as frozen as it gets. These are lakes of liquid ethane and butane. So it's basically lighter fluid. Let me click through here. Here's the first one that we found. This is, it's Ontario Lacus, so it's Lake Ontario. This one's at the South Pole. South Pole's down this little cross here. And yeah, so with our instrument, we can't actually identify what's in it. What we can say is that it is a suspiciously lake-like feature. That's what we like to say. But there are other instruments that can see what the lake is actually composed of, and the VIMS instrument shows us that it's liquid ethane, which is C2H6. Kind of like lighter fluid. All right. Now, that was the southern hemisphere. As time went on, the northern hemisphere became visible, and there's a lot of lakes up the northern hemisphere. This one here is the largest one. It's called Kraken Mare. It's about 1,000 kilometers from side to side. So from there to there is about 1,000 kilometers. And again, it's ethane. And over here on the right, this is an image that VIMS took while it was trying to study Titan's atmosphere, right? So here's the atmosphere here. And up here at the North Pole, there's this very bright dot. And they weren't doing this on purpose, but what it turns out they did was they accidentally caught the sunlight reflecting off of one of these lakes. And so we've got sunlight reflecting off of a lake full of lighter fluid 1 billion miles from Earth. All right. And so we've got, we have the lander, of course. I haven't talked about that yet, but here it is. This is an artist's rendition of the Huygens probe on Titan. And this is what the lander saw on the way down. So this is an image about 30,000 feet above Titan's surface. We jokingly say this is Titanian Airlines view a few centuries from now. And so you've got this kind of a dark, very flat, looks like a dried up lake bed. It's probably what it actually is. And then you've got a hill back here with lots of terrain features on it. And if you take these images and look at slightly different view, you can see all these channels. You've got definite fluid channels flowing into the lake. And so, yeah, this is clear evidence that it rains on Titan. Basically, it rains lighter fluid, but it does rain on Titan. so the the Huygens spacecraft landed down here somewhere, and this is an image on the right here. This is the image from the surface. And what this is that dry lake bed. And these rocks here, they're probably made out of ice, and they're about yay big, and they're a few feet from the camera. This is the exciting image from the surface of Titan. All right, and by the way, of course, at Saturn there's a planet. It's called Saturn. I'm not an atmospheres guy, so I hadn't talked very much about it, but they did have some interesting discoveries of Saturn's atmosphere. We actually lucked out quite a bit. During this mission, we weren't expecting to see a storm, because what happens at Saturn is we have a storm roughly every 30 years. It's pretty periodic. And the next one, we weren't actually planning to see one until 2020. And so we were kind of, hoping to see one, but we weren't expecting to. But we lucked out and we got one. And so that's what we got here, this image right here. And also there's so Saturn has jets like Earth, and it has a jet stream. But at Saturn, you get this standing wave pattern, and the jet stream turns out to be a little hexagon up here on top of the planet. All right. Sad stuff. Okay. So we're going to crash the spacecraft into the planet. So why are we doing this? Well, that is actually a very good question, why they're so infrequent. I'm actually not too sure. I've gone to some talks about how it works, but I'm not too sure I can actually explain it properly. It has to do with the distribution of water vapor in the atmosphere. You end up getting an instability that flips everything over every 30 years or so. All right, so we're going to end the spacecraft's life by smashing it into the planet. And the reason we're doing this, other than just saying it's cool to smash things into planets, is that if you take your orbits and you place them such that they're initially just outside the rings, like we've got here. These are called the F-ring orbits, and these are all done. And then you take your orbits and you place them between the rings and the planet, just what we've got here. Then what you can do is you can very, very carefully measure the gravitational field of both the rings and the planet. And so if you're a planets guy, this will help answer the question of whether or not there is a solid center to Saturn. So we believe that there is some rocky core at the center of Saturn, but we don't have any real evidence of that. And so we're trying to take measurements that will allow us to say whether or not that's true. And from a rings perspective, measuring the mass of the rings is very exciting, because we actually have very imprecise measurements of how much the rings weigh. We don't really know very well how much they weigh. And the weight of the rings is very important on telling you whether or not these rings are primordial or not. So basically, if the rings have a lot of mass, they might be primordial. They might have been there from the beginning of the solar system. But if there's little mass in the rings, they're probably not that old. And so we have to come up with some way of creating them, or some theory for explaining their creation. All right. And so this is just a close-up view of the orbits that we're doing right now. We are currently on this one right here, and in a little while we will fly by Titan, and we will be on this one, and you'll notice this one is red, and it doesn't continue out the other side. So that will be it. Yeah. And so with that, I will thank you for your attention, and be happy to answer any questions.
That was fascinating. So I've already got a couple of questions, a couple of good ones from the chat box. One I saw a couple of times is, what's the distance from the planet to the closest ring? How close are the rings to Saturn?
It's only a gap of about 100 kilometers.
Wow.
Okay. Yeah, it's really small.
Okay.
Basically what happens is, let me back up. Come on. There you go. Basically what happens is any particles that migrate inwards to the point where they're clipping Saturn's atmosphere will quickly burn up in the atmosphere. Okay. So they'll quickly deorbit and they'll end up in the atmosphere.
Okay. So about 100 kilometers. And what about the farthest ring? Or does that depend on how you define what a ring is?
Well, right. So it depends on what you mean, exactly. So the outer edge here is at, let's see, it's 2.4 Saturn radii. What's that? That's like 200 and... brain's not working. Yeah, like 160, 180,000 kilometers, something like that. Yeah.
I'm going to trust your math on that.
Yeah, don't trust my math. Yeah, let's look like that. The number that you want to use for comparison's sake is the radius of Saturn proper. So the radius of Saturn is about 60,000 kilometers.
Okay. Great. I saw a question early on, I believe it was from Rose, and it was, is the ocean on Enceladus salty?
We don't detect very much salt, but there is a little bit, yeah.
Okay, cool. Yeah. Great question, Rose.
Mm-hmm.
And another question, I believe, from Rose is she was wondering why the rings are so thin.
Oh, the rings are so thin because if you can imagine that there's any kind of vertical motion in them, what happens is they end up hitting each other. And so it quickly damps itself out.
Okay.
Yeah.
Cool. Let's see.
Rose got another one?
Yeah.
Rose is a Saturn expert.
I know.
I love it.
You're going to be able to let everybody in your library know everything about Saturn. Rose.
Yeah, that's right.
Why is there an edge? Why don't they just kind of fade out into the solar system? That's a good question.
Okay, the edges happen because of these resonances with moons. So what's happening here is this edge is confined by a moon called Mimas, which is why you get that elliptical pattern, and it's also why you get those mountains at the edge of it. This one is in a, what was it? It's in a resonance with Janus and Epimetheus? I'm trying to remember. I don't remember. It's also in another resonance with another moon. And so basically they're gravitationally confined by Saturn's moons.
Oh, very interesting. All right, and maybe we can take a couple of more questions. I know some of you guys probably have to get back to your circulation desk for story time. But yeah, if you have a couple of other questions, go ahead and put those in the chat box.
I'm going to ask a question really
yeah,
quick.
go ahead. Yeah.
So, Colin, you might have seen on Facebook, it was blowing up a few weeks ago, that NASA was hiring a planetary protection officer. Does the decision to do a controlled crash into Saturn have anything to do with that?
A little bit, yeah. Yes. So in addition to the science gains by doing these crazy orbits at the end, there's also the consideration that, there might be life on Titan, there might be life on Enceladus. If we run out of gas, we really can't predict where the spacecraft's going to end up. And so it's safer to just put the thing into the atmosphere.
Okay. Let's see. Rose, you're saying, but there's nothing beyond the last ring.
There's stuff all throughout the system, actually. The edge of this ring here has, there's a very narrow ring at the edge called the F ring, which is really dusty and very interesting dynamically. Outside of that, there's quite a bit more, actually. If you back up to the... Yeah, we're going way fast here. Here we go. Yeah, if you back up to the Equinox Mosaics, you can kind of see there's kind of material all over the place, right? I mean, it's not really dark anywhere. This really bright thing is the F ring that I was telling you about. It's bright because it's kind of like the same effect that, you know how if you've got dust on your windshield and you're driving around with the sun behind you, you don't notice? But if you turn into the sun, the thing can like blind you.
Right.
It's kind of the same thing. So little dust particles will tend to lighten things up like that. So that's the F ring. This little faint thing here, that's the G ring. This is another ring that Saturn's got. It's neat because it's got an arc in it. Like if you've heard of Neptune's rings, they have regions of the rings that are brighter than other regions. This one's the same way. It's got an arc in it. And then there's a tiny little moon in here that creates this ring, actually. And of course, the E ring out here, this is created by Enceladus and the geysers coming off of it. So there's really no point where there isn't stuff.
Before more people type and Gail's question disappears, she wanted to know if we've learned there it goes. If we've learned anything that'll tell us about the evolution of Saturn's future.
Yeah, I mean, so it's a difficult question because predicting the future is always with its hazards, right? But I've seen various simulations of what's happening to the F ring and whatnot, and one of the ideas that people have is as these rings expand, past the Roche limit, which is the point where things can start to coalesce gravitationally, maybe rings tend to form moons out there, which then kind of move away and whatnot. And there are a bunch of little moons. There's two of them near the F ring. There's one of them near the edge of the A ring, which they might be these pieces that have formed recently, in which case they'll start moving around and they'll be dynamically interesting.
Okay. So we have a couple of versions of the same question. When it crashes, are we going to be able to get any additional information from that crash, right, or is it just destroyed?
Yeah, they're going to be taking data all the way down. And so the geometry is not going to be good for imaging. We're not going to be able to take any pictures on the way down. But there's lots of those instruments that were designed to monitor the space environment. They'll be able to take readings directly of Saturn's atmosphere on the way down. And so the plan is to take the antenna here, point it towards Earth while we're smashing into the planet, and transmit the data as we're collecting it.
Okay, very cool. Mary, to answer your question, sorry you missed some of the webinar. We will upload it on YouTube, and you can view it afterwards. But I do not think your question was answered. Will there be a live broadcast of Cassini's finale on September 15th? I don't think it would be possible to have video of Cassini, but there might be some video of mission control or...
I have no idea. Yeah. I should ask.
They mentioned the answer to this question, and I don't remember what it was, in the Museum Alliance webinar that I mentioned earlier. So again, join the Museum Alliance, and they will have better information.
Yeah, I imagine there will be some kind of webcast from NASA. Of course, I think it'd be pretty hard, nearly impossible, to have a video of Cassini crashing, and I'm sure we'll see some cool artist rendering after that. Let's get one last question before we wrap things up. This is from Greg. The name sounds familiar. Has Cassini had any close calls in the past with hitting any objects during its mission?
There's been, I don't know if it's a close call. We've got a dust analyzer on board. We've got a few instruments in that analyzer that basically just count the number of particles that are hitting it. And during one of the plume passages, one of those broke. And so it's designed to pick up things, up to like 50 microns in size. And so we're assuming something fairly large hit it and broke it. But as far as the rest of the spacecraft is concerned, I don't know how you would tell. There's lots of stuff in the environment, and it's definitely hitting the spacecraft all the time. But nothing has broken other than that one instrument.
Okay, very cool. Okay, I keep on saying last question. This one's really good. Rose, are there any views of the rings from the top down?
Yeah. Actually, if you go to our website, cyclops.org, there's lots and lots of views for the rings from top down. We have orbits where the inclination is like 70 degrees, something like that. So, yeah, there's definitely lots of views of that.
Very cool. Yeah. So I hate to cut off the Q&A, guys, but after this webinar, I'll be sending you a lot of resources. I'll send you the slides uploaded to SlideShare. I'll send you a list of all the links, and you guys can just respond back to me, bmitchell@spacescience.org. And luckily, I work just a few doors down from this guy. Sometimes, because he's C. Mitchell, sometimes my mail goes
to his
mailbox. So just let me know if you have extra questions, and I'll go talk to Colin and and get back to you on that. Great questions, guys.
And also, while you guys are emailing Brooks all of your questions, like we mentioned earlier, this is kind of a new format for us, having a scientist in the room and doing a Q&A. If you liked this, please let him know, or if you have any suggestions for other NASA-related or science-related events or scientists you might want to talk about, do let Brooks know.
Yeah, please do. So I'm going to kind of start to wrap things up here, just issuing a few last reminders. You will be redirected to a SurveyMonkey link after this. And that's a great way to give us feedback to whether you loved it. We're going to assume you just loved it.
Don't break the model.
You might need to break the model. And
2 more weeks.
2 more weeks of this model, yeah. And so just give us any type of feedback through that SurveyMonkey link. When I close down the room, you will be directed that way. After you complete the SurveyMonkey link, there is another link to get your certificate of attendance. If for some reason that doesn't work for you, just shoot me an email. Again, it's bmitchell@spacescience.org, and I'll send that certificate of attendance directly to you. But there should be, you should be directed that way after we close out the webinar. Please, we would love for you to attend some of our upcoming webinars. We have some really, really, really great ones coming up over the next month or so, and we'll have more offerings after that too. You see our link here. If you would like to view our archived webinars, you can find them there. Follow us on social. That's a great way to get all of this information. So yeah, look for an email from me either later today or tomorrow, just kind of with a follow-up. Look for the YouTube version. Please share that around with your patrons. Share that around with your other library colleagues. And yeah, with that, I believe that's it from StarNet. So thank you guys so much. There's Anne. She's been in the shadows the whole time. And I will close out the room. You'll be redirected to that SurveyMonkey link, and just shoot me an email with any other questions. Thanks, guys.
I know.